Lidar. So it's not just about gathering the data. So here the core's brain, that is called control system. So this system is also needs to know where it is and what's going on. So it combines all the information from the sensors to create a clear picture of its surroundings. So sometimes the sensors might not be perfect, or they might give some conflict information. So that's where the real-time sensors processing techniques comes in. So these techniques help the core make sense of all the data. It can reduce the errors and be more confident in decisions. So ultimately, this sensors helps the car navigate safely on its own. So this is what sensors. So let's talk about the block diagram. So first one, sense, and then perceive and design and plan, at last act. So we will see one by one. So first, what is sense? So this part, it involves the sensors gathering the information from the vehicle surroundings. So this sense part can include camera, a lidar and radar and some ultrasonic sensors and others. So each of these sensors captures a different aspect of the environment. So such as detecting the objects and determining the distances or organizing the road signs. So next one is perceive. So what is perceive? So once a sensor have collected the data, so the vehicle system processes this information to understand what's happening around it. So this involves the interpreting the data to organize the objects like other vehicles, pedestrians, traffic lights and road markings. So it also assesses the speed and direction of these objects and predict their future movements. So this is what perceive. So next one, design and plan. So what is design? So based on the perception of the environment, the vehicle's computer, the vehicle's main system makes some decisions about how to navigate safely like that. So these decisions might include determining when to accelerate, when to brake, when to steer it or change the lanes like that. So the decisions are made by the algorithms that take in account of various factors such as the traffic laws or road conditions and behavior of the other road users also. So this is what design and plan. So after deciding on a course of action, the system plans a specific steps the vehicle should take to execute that decision. So this involves mapping out some trajectory for the vehicle to follow. So considering factors like lane changes, intersections and any obstacles in the path. So this is what plan. So finally act. So finally the vehicle takes action based on the planned trajectory. So this could involve controlling the steering, acceleration and braking systems to safely and navigate the road according to the decision made by the system. So this is all about the simple block diagram. So first we have to think and then perceive and decide and plan. At last we have to act. So this is what the block diagram. So let's talk about the sensors. What are all the sensors we use for autonomous vehicle? So first one, automotive radar and camera and ultrasonic sensor. Next, Lidar and then GNSS and GPS and IMU. So let's see one by one. So first, radar. So what is radar? So it represents the radio detection and ranging. So radio means it's like using the special waves we can't see to understand what's around us. Next one is detection. So detection is about sensing and recognizing things nearby like cars or people like that. So next one, ranging. So ranging means figuring out how far away something is. It's like using a special ruler but with invisible waves. So that is called ranging. So what is the main principle behind this in the sense? So these sensors working by sending out some invisible waves and listening for them to bounce back. So they use some different kinds of invisible waves to understand the environment around them. And also these sensors can tell if the things are moving or how fast they are going like that. So they are also really good at working when things around them change, like when it's raining or there is a lot of noise like that. So it uses the invisible waves to measure how far things are. So where they are and how far they are moving. So it can use different invisible waves for different jobs, like measuring at a 24 gigahertz or a 77 gigahertz like that. So it's good at seeing if things are moving, and it stays strong even if things around it change a lot. So this is the main principle behind this radar. And then classification of radar. So there are two classification types. One is primary radar and another one is secondary radar. So in this primary radar, we have two types. One is continuous wave, another one is pulse radar. And again, this continuous wave consists of the two, modulated and unmodulated. This pulse radar consists of two, MTI and Doppler. So let's talk about the one by one. So mainly this primary radar directly detects and tracks the targets using some reflected radio waves. So first one is the continuous wave radar. So it continuously emits a signal and it measures the frequency shift of the returning signal to determine the target's range. So this is what continuous wave radar. Another one is pulse radar. So what is this pulse radar? It emits the short pulses of the radio waves, and it measures the time delay for the echo to return to determine the target's range. So this is what pulse radar. So again, this continuous wave consists of the two. One is the modulated and another one is unmodulated. So the emitted pulse are modulated in amplitude or a phase to provide the additional information. So unmodulated is in the sense, so these pulses are not modulated. So next one is the moving target indicator. So that is called MTI. So it cancels out some stationary clutter and focuses on the moving targets by using the Doppler processing. So next one is the Doppler. So this Doppler radar, it detects moving targets by analyzing the Doppler shift in the returned signals. So that is called Doppler radar. So one more, this one is the FMCW. So that means frequency modulated continuous wave. So this FMCW, this radar, it emits a continuous wave with a frequency that continuously changes over the time. So this FMCW mainly used for the automotive applications, and this radar, it emits a signal with continuously changing frequency over a defined frequency range. So the reflected signal mixed with the transmitted signal, it produces some beat frequency that is proportional to the target range. So by measuring the beat frequency over the time, this FMCW radar can determine the target range and velocity and sometimes even angle also. So this is what the FMCW continuous wave. So mainly this one is used for the cruise control and collision avoidance. At the time we use this radar. So next one is the field of view. So what is the field of view? So FOV. FOV, it stands for a field of view. In simple terms, it refers to the extent of the observable world, so that a device or a sensor can capture or see at any given moment. So for example, in the context of the camera, the FOV describes the area or angle that the camera can see through its lens. So this is what FOV. So on the other hand, in the context of sensors that is used in autonomous vehicles such as Lidar or radar, FOV refers to the angle or range over which the sensor can detect the objects or any obstacles. So a wider FOV means that this device can capture a larger area or angle. And while a narrower FOV in the sense, it can only capture a smaller portion of the surroundings. So FOV is an essential parameter in various applications including the robotics, surveillance, and virtual reality and augmented reality. So let's talk about the 2D and 3D FOV. So what is the main difference between them? So 2D field of view. So in 2D, the FOV typically refers to the horizontal and vertical extents of the observable area that captured by a sensor. For example, In a camera, the 2D FOV would specify the width and height of the image or a display area. So it's like looking at a picture on a flat surface where you can see how wide and tall the image is. That is what 2D FOV. On the other hand, 3D FOV. So in 3D, the FOV describes the entire volume or a space that a sensor can perceive in 3 dimensions. So this includes not only the horizontal vertical extents but also the depth or distance from the sensor. So if we take a Lidar or any radar system that is used in autonomous vehicle, this 3D FOV specifies the range of distances and angles over which objects can be detected. So this is what the main difference between the 2D FOV and 3D FOV. And let's talk about the SRR and MRR and LRR. So first, SRR. So that means a short range radar. So typically it detects objects within the range of around 0 to 30 degree. 0 to 30 meters. That means 0 to 100 feet from the vehicle. So up to 50 meter. So it can detect. So can cover a field of view of approximately 90 to 120 degrees. So that is what the short range radar. So next one is the MRR. So what is the MRR? MRR is the medium range radar. So it detects objects within the range of about 30 to 80 meters. Up to 100 meters. So that means 100 to 260 feet from the vehicle. So it covers the wider field of view compared to the SRR. So it's typically around 120 to 180 degrees around the vehicle. So next one is the LRR. So LRR is basically about the distances, it detects the objects at distances that ranging from 80 to 260 feet up to, so up to 250 meters, up to several hundred meters away from the vehicle. So it covers even wider field of view compared to the SRR and MRR. So it's often spanning to 180 to 360 degrees around the vehicle. So in a simple terms, this SRR, it detects the closest to the vehicle within a short distance range, and MRR, it detects objects at a medium distance range, and LRR can detect the objects at a longer distance with the widest field of view. This is what the field of view, simple terms. So this is the range of our different SRR and MRR and LRR. And then why radar? So there are a lot of reasons we choose radar. So first one is the Doppler speed measurement. So radar can tell how fast something is moving. It's like a pedestrian or a car on the road with just one measurement. It's like knowing if something is speeding up or slowing down. So next one, the radar can figure out how far away something is and what angle it's at. So it knows exactly where objects are positioned. So next one, this radar can also tell what type of object it's seeing by measuring its radar cross section, and it's like recognizing the shape of something by its sensor. Next one is the radar works really well even when the weather is bad. It's like when it's foggy or rainy or snowy like that. So it's having a special vision that can see through the tough weather conditions also. So that is why we need a radar in our autonomous vehicle. So next, this is the automotive radar applications in autonomous vehicles. So first one is the adaptive cruise control and forward collision warning and forward cross traffic alert turn assistant and blind spot detection and vehicle exit alert and rear cross traffic alert. So next we are going to talk about the camera. So camera, we know the camera uses some special sensors that don't emit light but capture the light that's already there. So to create a picture of an area, so it's like taking the photo with your phone. So it's like having eyes that can see both the things that are moving or things that are not moving. So camera are usually affordable and easy to find because they are used in many devices like smartphones and security systems like that. So next we will see the types of camera. So first one is the monocular camera and another one is the stereo camera. So what is the monocular camera? So this monocular camera is a type of camera that uses a single lens to capture the images. It operates much like the human eye. So which uses a one lens to focus the light onto the retina at the back of the eye. So this monocular camera are commonly found in everyday devices such as the smartphones, digital cameras, webcams like that. So this monocular camera, it provides a single perspective of this scene they are captured. So they record images in 2D and the meaning they do not provide the depth information. So as a result, these objects in captured images do not have sense of the depth or a distance between them. So these monocular cameras are suitable for the various applications including the photography and video recording and surveillance like that. So next one is the stereotype camera. So this stereoscopic camera is also known as a 3D camera. So this camera consists of two or more camera lenses that position to the spacing between the human eyes. So by capturing from slightly different perspectives, this stereo cameras to create a sense of depth and enable the perception of three-dimensional space, 3D. So these stereoscopic cameras work by capturing the two separate images, one for each lens and which represents the views from the left and right eyes. So these images are then presented together to create the stereoscopic effect that's simulating the way human eyes perceive the depth. So mainly the stereo camera commonly used in applications where the depth perception is important, such as VR, virtual reality, and 3D movies and medical imaging like that. And this is what the main difference between the monocular camera and stereo camera. Next one is the disparity. So what is the disparity? So this formula is derived from the basic principle of a similar triangles in the geometry. So F is the focal length. Here this is a formula, Z equal to F dx divided by D. So F is the focal length of the camera. It represents the distance from the camera's optical center or a distance from the lens to the image plane. So the image coordinate of a point in the image. So in the pinhole camera model, so this is typically represented in the pixel coordinate. So Z is the depth of the point in the scene. So that measured along the camera's optical axis. So here the formula relates the depth Z of a point in the scene to its image coordinate X in the image plane, and it derived by considering the similar triangles formed by the camera's optional axis. So the distance from the camera to the point in the scene and the image plane. So this is what Z focal length baseline divided by disparity. So these are the applications of cameras in autonomous vehicles. So first one is the traffic sign recognition and speed limit recognition and blind spot detection and 360-degree surrounding view system, lane detection and lane keep assistance systems and object recognition systems. And we will discuss about the ultrasonic sensor. So what is ultrasonic sensor? So these ultrasonic waves are sound waves with frequencies higher than the upper limit of the human hearing. So it's typically about 20 kilohertz. So these waves are used to measure the distance to an object, sending out the sound pulses and measuring the time it takes for the echoes to return. So this method is known as the ultrasonic ranging or a sonar. So this is the short ranging applications. We know the ultrasonic ranging is commonly used in short range applications such as the automated parking systems and any obstacle detection in robotics. And these systems provide the accurate distance measurements over a relatively short distance, typically up to several meters. So these ultrasonic waves are a high frequency sound waves that mainly used for distance measurement and object detections in short range applications. So ultrasonic sensor mostly used for the parking assist. So these ultrasonic sensors are like a special ears for the cars. So they were first used to help the drivers to detect any obstacles while parking, but now they are part of the automatic parking system. So mainly these sensor helps and control the steering, acceleration and braking of the vehicle to help it park automatically without mounting and detection range. So these sensors are placed rear on the rear bumper of the car. So they work like eyes that can see obstacles up to 2 to 2.5 meters away behind the car. So this one help the car know when it's getting close to something and needs to stop or changing the direction to avoid hitting it. So by using a higher frequency and adjusting how much the sensor amplifies the signals at noticing objects on the ground like wheel stoppers like that. So this helps the car park more accurately and avoid bumping into things that are lower down like curbs or barriers. So this is driver hands on the wheel. So next one, we are going to talk about the most important thing, that is the Lidar. So what is a Lidar? We know Lidar, it stands for a light reduction and ranging. So Lidar is like a special sensor that measures the distance using the light. So it's a technology used in things like self-driving cars and mappings. So this Lidar uses sensors that send out their own light to see the surroundings instead of only on natural light like our eyes do. So it creates its own light source. And this Lidar sensor spins around continuously. So kind of like a spinning top. So they shoot out thousands of tiny laser beams every second. So this is a diagram of this Lidar. So these laser beams go out in all directions around the vehicle. So this is what the laser beams, it hit the objects in the surroundings like buildings or trees or other cars. So when they hit something, they bounce back. So by measuring how long it takes for the laser beams to bounce back. So the Lidar can figure out how far things are. So Lidar is the one kind of the moving technology that uses its own light source to measure the distance, and it sends out thousands of laser beams in all directions. So which bounce off objects and come back to the sensor. So next one. So point clouds. So what are the point clouds? So here you can see these are the point clouds. So this point clouds are like a 3D maps. So that made up of millions of individual points in space. So each point represents a specific location in the environment. How they are used. So the point clouds are used to understand and visualize the surrounding environment of a vehicle. So they are created using technology like Lidar, which scan the area and record the distance to objects by measuring how long it takes for a light to bounce back. So these point clouds help the vehicle sensor detect and recognize the objects like other cars and pedestrians and any obstacles. So it's having a detailed map of everything around the vehicle in 3D format. So by analyzing the points in the point cloud, so the vehicle system can identify any objects and determine their positions and sizes and shapes. So this information is very crucial for making the decisions such as avoiding the collisions or navigating through traffic. So these point clouds are 3D maps are made up of many points in space that created by the technologies like Lidar. So mainly this Lidar is behind the principle is TOF. That means time of light. So basically Lidar works like a stopwatch. So measuring how long it takes for a light to bounce back from the objects. So mainly this helps it figure out how far away the things are. And a good Lidar scanner shoots out of 8 to 128 laser beams in all directions to create the detailed 3D map of the surroundings. And these laser beams, it hit any objects and bounce back. It collects the bounce back data to create a picture of everything around the vehicle. And this lidar works together with the GPS to make sure it gets things right. So this GPS provides ground truth data. It's like a reference point to check if lidar's measurements are accurate or not. So this helps validate the performance of the other systems in the vehicle like camera, radar and ultrasonic sensors. So this lidar can spot even small objects around the car also, like the pedestrians or any debris on the road. So mainly this lidar uses the time it takes to it takes for the light to bounce back from the objects to create the 3D map of the surroundings. So next we will see about the GNSS and IMU. So what is GNSS? So GNSS is like a super navigation system in the sky. So it uses the satellites to provide the precise positioning information all around the globe. So GPS, we know that is a global positioning system. So GPS is a part of a GNSS. So it uses a network of satellites to pinpoint your location on Earth. And next one is the GLO, GLONASS and Galileo and Beidou. So these are the other satellite systems that work along GPS to improve the accuracy and coverage. So they are like a backup systems that make sure you always have a clear signal no matter where you are on the Earth. So this GNSS provides very accurate location data, so down to few meters. So mainly this GNSS is used in autonomous vehicle to figure out where they are and where they are going. So it's like giving the vehicle a built-in map and compass so it can navigate the roads and reach its destination safely. So mainly GPS to determine the precise location. So to figure out exactly what they are on the map. Next one, it calculates how fast they are going and which way they are headed. And then navigate along the predefined routes. So this autonomous vehicle followed the predefined routes using the GPS guidance. So it's like following the directions on a map to reach a destination. So, but the AV does it automatically, so using a GPS coordinates to stay on the course. So, next one is the IMU. So, what is an IMU? So, it stands for an Inertial Measurement Unit. So, IMU is like a special sensor package that combines the different sensors to measure how an autonomous vehicle moves. So mainly it includes a sensor to measure the acceleration, that means change in speed, angular velocity, rotational speed, and then orientation, that is direction the vehicle is facing. Next we have to estimating the vehicle motion and heading and tilt. So this IMU uses data from these sensors to figure out how the vehicle is moving, which way it's facing, and if it's tilting or leaning like that. So next one, fusion with GNSS data. So the data from the IMU is combined with data from the GPSs to improve the accuracy. So by combining these different sources of the data, the vehicle can get a more precise and understanding of its position and speed and direction. So it's like cross-referencing your location on a map with the movements your body senses to make sure you are staying on the right path. So that is what the IMU, Inertial Measurement Unit. So next one is the very important topic, that is the sensor fusion. So what is the sensor fusion? So we know sensor fusion is like a teamwork for the sensor. It processes where the data from this different sensors like camera, radar and Lidar and GPS work together to give a more accurate and understanding the environment. So it's like having a multiple people with different skills working together on a project. So each person brings that unique perspective, and when combined, they create a more and complete picture. So the same principle works here, and it can merging the sensor fusion combines data from the various sensors to create a more precise understanding of a target or objects. And we are creating the comprehensive view also by merging the data from different sensors. So this fusion helps to create the comprehensive view of the environment. So why sensor fusion is very important? So this sensor fusion, so it creates a single and accurate picture. So we know it combines the data from the multiple sensors to create a single or undefined unified image or a model of the surroundings. So each sensor has its strength and weakness. So for example, cameras are good at capturing the visual information while Lidar provides the accurate distance measurement, and by combining these data from a different sensors, so sensor fusion can compensate for the strength and weakness. And this fusion process use some algorithms also, some software algorithms to analyze and integrate the data from different multiple sensors. So mainly this one, it helps to provide a more comprehensive and precise understanding of the environment. So this is the sensor fusion, and this one is the sensor fusion approaches. So here there are three approaches. One is the data level fusion, another one is the future level fusion, another one is the decision level fusion. So what is the data level fusion? So mainly here the raw data from the multiple sensor is combined into the single data set before any processing occurs. So here this approach, it involves merging the raw sensor measurements such as images from the camera or point clouds from the Lidar and signals from the radar into a unified data set. So after this fusion, so the algorithm can analyze these combined data set to extract the relevant information about the environment. So this data level fusion is like mixing the different So this data level fusion, it's mixing the different ingredients together before cooking a meal. So it's like that thing only. So next is the future level fusion. So this future level fusion, it involves extracting the specific feature or characteristics from the data provided by each sensor and then combining these features into the single representation. So this approaches identify some key features such as the edges from the camera or objects in point clouds from each sensor's data. So these features are then combined to create the fused representation that highlights important from all the sensor. So next is the decision level fusion. So decision level fusion, so mainly this focuses on combining the decisions or outputs of individual sensors processing some algorithm, so rather than the raw data itself. So each sensor independently processes its data and making the decisions based on the predefined criteria or algorithms. So this is all about the sensor fusions. And next one is the algorithms. So here these are the major algorithms to use in sensor fusion. So first one is the Kalman filter. So we know the Kalman filter, it's like a small organisms. So they use some mathematical equations to predict an object's current state based on the past observation and adjust the predictions as a new data comes in. So it's like predicting where a moving object will be next by considering its speed and directions. So next one is the deep learning based approaches. This deep learning is a super smart students. It uses the Neural networks, so which are the computer systems that inspired by the human brain to learn from large amounts of data and making the predictions or decisions. Next one is the graph-based approaches. So this graph-based approaches are like a maps with connections between different points. So they model the relationship between the objects or a data points as a nodes and edges in a graph. So it's like understanding how different pieces of information are related to each other and using those connections to make the decisions based on that. So these are the important algorithms in sensor fusions. And next session, we are going to talk about the visualized sensor coverage